so the name of this panel is Open Mic. And Luigi, where are you, Luigi? There. Way in the back?
Yes.
That's to make sure that I don't get you up here. So there were 5 topics that were suggested. So, that's right, so you were wrong. And so I'll read them to you. So I think the thing to do is to have the topic introduced by the person who wants the topic discussed. And I like the idea of open mic panel, because that way we have no agenda. It's whatever you guys want to talk about. Most good panels I've been on over the years, you know, you start with people making their comments, and then the audience starts asking questions, and you know, it has nothing to do with the comments that the people started with, and it goes off.
So that's the title for tomorrow.
Huh?
No agenda.
That's the title for both today and tomorrow. Oh, I see. Today's open mic, tomorrow's no agenda. That's good.
You don't listen to no agenda newscasts.
No agenda newscast.
You've never heard about it.
Huh? Is that a British thing?
LA thing.
LA thing. No agenda newscast. I think that's good. So the 5 topics, I won't, so I'll just tell you what they were. The first topic was multi-core. I don't know how to make a topic out of that.
Don't surprise me.
Then the next topic was the publishing culture in computer engineering, which I guess I talked about on one of the beach notes a couple of years ago. But there's a lot more that can be said. It'd be much better to have it as a dialogue just rather than listening to me rant. And then one guy came up to me this morning and he wants to talk about concurrency control for synchronization and multi-core. And then another guy says, you know, what do we do about memory? It consumes all the power and the area, and we have absolutely not solved the memory problem. And then the 5th topic was, is this the end of general purpose processing? So which one should we do first? What do you think? And I think what we do is we have the person who recommended the topic get up and introduce it, and then we will comment if we feel so inclined, and then let people speak. We have a mic over there, right? Right. So, of you 5 guys, is there anybody that wants to go first, or does somebody think that they have a topic that is
Not on the list.
not on, that's right, not on the list, that is more interesting to discuss? Nobody's gonna get up.
Give the mic to Luigi.
The one you suggested you.
I'm sorry?
The one you suggested you.
Which
The one you suggested.
Yes.
Well, come talk about it. Which one?
The one you said yes to, Trevor. The one on 10
I've
years.
been drinking heavily, I can't remember.
This was late last
Stop
night.
the recording.
I can't, don't worry.
This was-
It's about past 10 years on computer.
Oh, you want to discuss that?
Okay,
We don't want to start with that.
I don't know.
Do we want to start with that?
If Luigi's prepared to give it a preamble,
I guess that's okay. If
Leave
we-
that for tomorrow.
Okay, go
Let's
ahead.
start with the
Preamble.
5 nice ideas.
I'm
Let's
sorry?
start with the 5 nice ideas that people came up with.
So what do you want to do? You want to talk about yours, or you want to talk about one of these 5 nice ideas?
No, I want to talk about mine tomorrow. Today, I want to talk about these 5 nice ideas.
So 5 nice ideas is today, and then yours is tomorrow.
Okay, let's do it. Is anybody going to volunteer any?
Okay, I'm going to just pick on one. I'm going to volunteer one of them. Nobody gets up, unless somebody has a 6th topic they want to talk about. And we'll get them, the 5 of them squirming. So I think I'm going to pick on Andy. You got it.
Thank you.
Well, I think that's a good topic. So we got to grab the mic.
I don't need a mic. I don't need a mic.
Well,
You don't need a mic.
Yeah, those guys need.
Okay. What do you think? You're Trevor Mudge or something? You don't need a mic.
I guess so. So
what is clear, I think, is that systems are becoming more and more heterogeneous.
Okay, so
Yeah.
that's your.
So, I mean, we have seen the talk of Alex this morning. I mean, even supercomputers are getting heterogeneous. Well, the area of embedded systems has, I think, a longer history in heterogeneous systems, and programming is a big issue there. Maybe a bigger issue than in homogeneous systems. And Alex this morning basically focused on the hardware, which is nice, but and sometimes he mentioned something about programming that is very hard. But that's sort of an understatement, I think. It's impossible, I think, to program these big machines. And I think in the embedded domain, okay, I'm not saying we solve the problems, but I think we are slightly doing better. Because, I mean, we don't have the general purpose problem, yeah? So we have, well, fairly well-defined application domains. And for these application domains, we can use different models of computation. And by exploiting that, we are, I think, better able to do the programming of these kind of systems. So my question is, maybe a statement, is if these sort of other, well, the more traditional general purpose machines are becoming more and more heterogeneous, I mean, should they look at what we have been doing in the embedded domain? And so that's basically you have to decide on different application domains as well, rather than trying to solve the problems for the entire domain, which is, I think, impossible. Let's hear it.
So, what do you think people like Alex can learn from you? You being embedded people, not just you, not just that, but you plural.
Well, maybe someone else would like to answer.
And also from the embedded domain. I think what we did in embedded systems for years already, that we had restrictions in our systems, either memory or power or whatever. And in the supercomputing domain, there were hardly any restrictions. So they could do anything. And in the embedded domain, we were restricted by type of applications, but also the power constraints or chip area constraints. I think that's what they can learn from the embedded system.
So maybe another thought. I mean, Alex showed two types of top 500 lists. So one of about performance, the other one about green computing. But what I missed there is productivity. So in my view, there should be a third list.
A third what?
A third ranking showing something about
Productivity
how easy is the thing to program.
Well, you heard what Alex said. He said WinPack has made memory bandwidth and interconnections irrelevant.
LibPack is not an application.
You are interrupting me in the middle of my
Congratulations.
What Alex said was WinPack has made memory bandwidth and interconnection networks irrelevant.
I'm not sure what he said.
I would say that therefore WinPack is irrelevant. The other thing that Alex said, which I wanted to take issue, was that he says that you know, we're going to go from what? We changed the first letter, so we go from T to P and now P to E, right? Terra to Petha to Exa. To, I think Trevor taught me this morning that the next letter is Y, which doesn't stand for Yale, it stands for Yota, see? But it's not about power. It's about how many dollars or euros you have to waste. If you want to be number one, it's all about the dollars. Right?
That's productivity.
Wasting dollars is
Well,
productive.
maybe not for the supercomputing domain, but for other domains it is.
Sure. I think you're correct. I'm not sure that the supercomputer community has been very conscious. I mean, they spend a lot of time handcrafting the software.
They do what?
spend a lot of time, you know, trying to use these machines. They're not naturally programmable.
For good reason. They're optimizing on this silly benchmark.
Well,
If you don't care about memory bandwidth,
you're getting hung up on
if
that.
you don't care about memory bandwidth, you don't care about anything. So, you know, so
I
people
don't-
are
I don't
talking
think
about
that's
Moore's
really
law
true.
is now doubling the number of cores on the chip, right? Yeah. No interconnection structure, by mental telepathy, they talk to each other, right? It's silly. But I'm getting far afield. You would like to have a different computer for every application? Is that what you're advocating with your?
So maybe sort of an underlying platform which can be customized to different application domains.
Ah, good. So the first thing you might want to do is put an accelerator called a floating point multiplier on the chip. And then you introduce into the ISA floating point multiply as an opcode. See where I'm going with this or not? Yeah. So that's the chip of the future, right? That what the embedded space has said is that we can build any tailored piece of functionality to do a particular job. And the reason why embedded work so well is because, in fact, I think you said it, is that your domain is sufficiently restricted. That's why VLAW works so well in embedded, it doesn't work in general purpose, right? Because VLAW is really nothing more than horizontal microcode of 30 years ago, right? You need a restricted domain. So why is that not the answer? That is, you have this platform, like you said, platform, and now you have all these accelerators to handle the specific task that needs to be done.
So,
But now you need the algorithm person to actually talk to the microarchitect to know what's on the chip.
but what are the application-specific blocks that you stick on a supercomputer,
So I think on a supercomputer?
apart from a floating point unit?
On a supercomputer? Why does it have to be a supercomputer?
No,
Actually, now what they're doing
we're
is
talking
sticking.
about what they can learn from
The embedded domain.
the embedded
Oh.
domain. So the embedded domain has sort of pushed the idea of application-domain-specific things, right? You know, you have codecs on there, you have.
So already they've discovered GPUs, right? Because they can get the supercomputer.
Well, because supercomputers.
So they, yeah, with me, you know, with a GPU,
There's
you
no-
can really make Linpack run like crazy.
So in the last 10 years, all it's done is basically take commodity parts. I mean, it's been heavily dependent on commodity parts, right? Because of cost. Actually, you want to put a gazillion things in a box, it's easier to get off-the-shelf parts to do that, right?
I think basically with the multi-cores now, we're going to have a few cores that do the regular stuff, like I/O, operating system, etc. And then basically have different accelerators for each application.
Isn't that what a SOC is?
Isn't what it was?
Right.
What?
System on a chip.
Yeah, basically, but
Oh, man.
you know, sitting next to Yale.
No, I didn't hear what Trevor just said. Isn't that what a SOC?
Well, I'm just going back to.
Oh, a SOC.
How are you going to program them?
Well, you're supposed to know that. You've been working on that for 10 years. Come on.
We're in the
So
middle.
now it's our problem.
Actually, sitting next to Yale, I got a crazy proposal. How about if we build,
Osmosis alive and well.
yeah, how about if we just build a Linpack supercomputer, only Linpack, just hard code it to do Linpack, then we'll always win, and we'll stop this from being the benchmark. Why cannot do that?
So that may be the way to get rid of Linpack.
Yes, I mean, that's it.
So you know, in a different
Nothing
way.
else, just Linpack. Just hardware like, you know.
I'm happy to hear that, Skevos, because this was the crazy idea. You can find it on our webpage since 2005. We're looking for a few bright MSc students to build a couple of
Linpack
tens
itself.
of FPGA boards connected together, the link makers.
Yeah.
That's why I did not see it, you said practice.
Yes, that's why I
I
didn't.
don't qualify.
FPGA,
Yes, FPGA.
and that's gonna win
That's
on
gonna
which?
slow.
Area, time? I can't
No,
remember.
no, it's gonna be doing very well and very powerful.
But you don't need FPGA to do impact, do you? I thought impact is well understood.
Oh, of course. Yes.
No, but I like Skevos, so about 20 years ago, I was involved in design of, I think it was the first Prolog machine. And there was the WinPack equivalent in the Prolog world. So I don't know whether you know about Prolog?
I know about Pro.
Yeah, so you know what the WinPack equivalent of Prolog, yeah, it was called the determinant concatenate. What you did is you took a string, and you concatenated the two strings. And if you want to do it in a general purpose Prolog kind of code, so what they're measuring is not megaflops, but rather lifts, logical inferences per second. And it takes a lot of them. On the other hand, if you can recognize that the program is determinant concat, that's all you have to do is copy this string over here and you're done. And you can go through the roof. So that's what we did. Off to the side, we had the ability to take this silly benchmark and just copy it and get the benefit
So
of it.
maybe we should ask Alex what application-specific things he wants to do.
That's the problem, is that you can no longer afford to give us an application-specific supercomputer. 10 years ago, you built a computer to run mainly one application, and then you use the spare time to run other things. So ASCII read was intended to replace nuclear detonations. Okay, the Earth simulator was intended for climate modeling. Okay, but you can no longer afford to do that.
So what features did they have for those particular applications?
Well, I guess the process, I mean, the ASCII read did not have any tuning to the application, I guess. Because it was built from commodity components. The Earth simulator, I assume, had the vector processor pipeline tuned to the requirements of the weather forecasting model that they were running. Okay, even if it achieved 80-something percent efficiency on impact. Okay, but doing application-specific supercomputers would be too expensive. Okay, Yale was putting the example from my point of view. It's an obvious accelerator that you want to put on the chip. Okay, so what's the next obvious one you want to put there? Okay, the further you go down the chain, the less applications are going to use it. So there's a break point where adding an accelerator is essentially wasting space there, making the chip more expensive for no actual reason. Okay, so being application specific gives you a huge advantage. Knowing that you have to run a number of applications with scientific models that can change from one year to the next.
So this thing that uses the GPUs, the Chinese machine, do they customize those, or they just?
No, it's commodity component, it's probably.
Yeah, so I think
So they have like the texture memories in them and things like this? Things that they want.
They do texture memory with the GPUs? With the
They
general
have
purpose?
things that they don't, I mean, what do they use them for?
I have absolutely no idea what applications they run there.
So they're running any applications, or, so I've always been under the impression that the reason why you guys have gone to the GPU is because, you know, it's SIMD and it's also SMT, which means there's tremendous opportunity to do impact fast. Right?
With less power.
So
And it's
GPUs are nice for
strictly
certain
that,
set
you can do
of
impact so
algorithms.
much faster with a GPU.
Okay, GPUs are one example of that. I mean, they're extremely efficient, they're extremely powerful for a certain set of algorithms. But there are other algorithms, sparse matrices and such, where they will not give you any advantage. So, how general purpose do you want to be? That's why there's the Jaguar, there's Skate, which is still trying to maintain the homogeneous multi-core view, because they want to remain high productivity and general purpose. The moment you start adding accelerators, you're saying, I want these kind of algorithms, but not these kind of algorithms.
So what is it they can learn from the embedded space in the dimension of power? They obviously need to be a key. They're sort of broken up to the fact they can't continue to pump endless quantities of energy into these things.
Basically, I found a very interesting trend in Alex's presentation this morning. So the machines that he was presenting, there was the following trend to be seen. When you report less power, right, when the system was more heterogeneous, you are immediately saying, but programmability of that thing becomes an item. And of course, that means that basically you have to have this trade-off of, right, how much energy you want to waste, basically, to do computation, and as a trade-off was how much effort you should do in order to program your machine. And there must be some optimal point. And of course, they hit that wall when they found out that they cannot basically waste this energy and the bill is rising out of the time. Right, Alex?
That's another difference between the supercomputing community and the embedded community. In embedded systems, users are more than willing to rewrite their application to optimize for the platform. In supercomputing, it takes 10 years to develop an application, then you use it for another 10 years, and then there's a decline period of maybe another 10 years while you overlap it with the next.
So how did you get people to buy into using GPUs?
Because they promise an enormous speed up, okay, as in a couple of orders of magnitude, okay, and that's reason enough to push people to try. Okay, if you offer people a 2x speed up, they're not touching their code base. You offer them a 10x speed up, well, maybe I can think about it. If you offer them a 100x speed up, then they will look into it.
So they'll accept the CUDA pay.
Yeah. Some will. Okay.
And the CUDA pay and the,
Think that most supercomputing applications are still written in Fortran. Okay, for which there is no CUDA.
and so CUDA works for applications or for a very small subset of applications?
I'm going to say subset of applications. I'm going to quantify this.
Those applications that don't have branches, for example.
You can have branches and it will still work.
Divergence kills performance dramatically. The fact of what? That if you've got a warp and there are 32 threads that are going and you hit a branch, some subset goes this way, some subset goes that way, you've just lost half the performance because now you have to run it through for this and then run it through a second time for that. If in running it through, you hit another branch, now you've gone down to 25% of the performance. So branch divergence is serious. The other serious thing, as you know, is memory. It better be that these 32 all hit the memory system and don't cause bank conflicts.
But
Right.
it's not just that. I mean, you need all 32 or all 1,000 of them to attack the same working set, to attack the same very small working set.
But they have to attack it without bank conflicts, or else you're going to stall waiting for each of these memory. It's not okay to have 32 and say, okay, 1, 2, 3, 4, 29, 30, 31, 32, okay, that load is now done, right? So you have to deal with that, the organization of memory. I think they coined the term memory coalescing to refer to that. So the CUDA thing works, or it works on a very small subset of, we're not talking about graphics applications now, we're talking about what historically are supercomputing applications.
Well, it works nicely for the same kind of applications that used to work in the gray vector machines, okay, where memory coalescing was still the same problem. You still had to deal with memory conflicts and such, so the same set of applications, the same set of solutions sort of applies, okay, which is still a restricted set. That's why multi-cores are so much more productive than vector computers, because they're easier to program.
I have a question that I've been asking people, Alex, maybe you are the one who can answer. The vector computing, you know, we're old enough to go through the vector computing. So if we just take that class of application that's solved by vector computing, so what percentage of the supercomputing needs do we cover? Except, let's leave the sparse matrices on the side because it can be solved with other ways efficiently. If we can go back to the 80s and get that type of vector computing in a more efficient way today.
The answer is going to change dramatically from one supercomputing center to another. Okay? Within Europe, we've had the DICE infrastructure initiative, now we have the BRACE infrastructure initiative, and there's one effort they're trying to put together a benchmark for supercomputing. Okay? That's something that's not impact based on what applications we actually use. And it turns out that from the application set that we use in Barcelona to the application set that runs in Julie, there's an overlap of only one application. So I'm not capable of telling you what percentage of the supercomputing applications would be well supported by vector computing.
Because I remember when I was attending as a graduate student ICPT, they were saying in order to large applications have to be symmetric. So all large applications are symmetric, so that's why the SIMD, etc. was efficient and the vector operations were efficient. Now I know we're getting into new type of applications, but my question is how many of those are, like you said, most supercomputing applications are in Fortran. If they're in Fortran, that means it's easy to put them in a form and they can be handled by accelerators. Because Fortran was doing just array manipulations.
So the answer is supercomputers cannot make much use of application-specific accelerators.
Or I would say there's not much future for chips that have application-specific accelerators. Okay, having an accelerator that's a secondary chip that you can customize your PCB to it, that's much cheaper, and that may happen. Okay, and you see there's some efforts out there. Some of the fastest and most efficient supercomputers are application-specific. Okay, we had a keynote here, I think either last year or about an application-specific machine. I don't know if maybe I'm confusing it with computing computers.
So how about if we slice it differently? So what I get from you is that you can't afford the accelerator. You say, well, why can't you afford the accelerator? The chip has billions of transistors on it. In fact, we're going to have 50 billion transistors on a chip before too much longer. Why can't we afford accelerators? Well, the reason is because we want to use those 50 billion transistors for more and more cores. And so we'll get 1,000 cores on a chip, and then WinPack will go, even more fantastically with 1,000 cores. So how about a, huh?
I said, somebody needs to unlock your brain from this thing.
Let's stop talking about it. Look, Alex just said it, I think, that only one application overlaps between two supercomputers.
I thought his comment this morning was fantastic. That WinPack makes memory bandwidth and interconnection networks irrelevant. And I would argue that that makes WinPack irrelevant. But no, they're still measuring it. No. So when was the last time the top 500 list came out?
It comes up every 6 months.
That's right. So when was the last time it came out?
June.
June. And what did they use as the figure of merit to determine the ranking? WinPack. Good. I rest my case on
Well,
that one.
the embedded world has its own distortion.
So I am about to make a point.
What do you use?
You keep citing Drystone.
Drystone.
Not you particularly.
Drystone?
No, if you look at all the manufacturers,
Drystone
of
silly.
embedded microcontrollers.
Actually, that is a problem of our domain. because-
Drystone?
No, we don't have a single or a set.
Well, Drystone is silly.
We don't have
We
any.
know.
I'm just trying to give you something
No,
else.
Drystone's even worse.
Get off the list.
Get off the lid back, get off the Drystone.
Drystone is worse than WinPack.
Yes.
There's no input data in Drystone. So therefore you can compile the thing out to one instruction, write the answer, right?
And then you get a huge dry still now.
Look up there.
Everybody has something to hide under the carpet.
Everybody? Yeah, everybody. All right.
Even you, yes.
So let me make this point, because I've wondered about this for a long time. Instead of trying to put more and more cores on the chip, which is what's going on, right? We already have, I don't know whether they're products yet, but they're so close to being products, you may as well say they're products, 32 cores on the chip, right? It's gonna go, we will have 1,000 cores on a chip. And WinPack will run much faster because each one of those cores will do these simple operations. How about if the individual core, if the individual chip is embedded processor with the set of accelerators on it, which can be powered off when not needed. And now we use that other dimension. You know, we talked, so Alex talked this morning about 762, I forget what he called them. What did you call it? Racks, yeah. 762 racks. So the chip becomes a core with all the accelerators, and in the other dimension, we have the number of cores. And now we got this humongous thing that can, you want to be doing, I don't know, some fast Fourier transform, fine, you've got the fast Fourier transform accelerator on each one of the chips that can do it. You want to do a database kind of thingy, then you can replicate that. Now what you've got is this huge, now what you got is this huge system, right? Because you haven't packed a huge number of cores on each chip. So you're expanding in the direction of chips.
Well, I think that this AMD Fusion program is attempting to head in that direction, although it's a little unclear what they're doing.
They're doing one-on-one or something? We're talking about, I don't know, how many cores on, so the number one 500, how many cores?
84.
Huh?
84.
No, how many cores?
Total.
Yeah. On the number one 500.
I have to check my notes.
So it's like 10,000 maybe?
130.
100,000?
I think it was 130 if I was Alex.
Which is a lot bigger than 2, right?
I'm going to say it's,
Huh?
yes, it is.
So you think that core fusion is a step in that direction?
No, I'd say it's an attempt. I'm not endorsing it, I'm just,
Well, just a comment to the proposed architecture here. I mean, the architecture you're describing already exists. I mean, it's the Texas Instruments OMAP 5. It comprises, I think, 15 different programmable cores comprising in total 11 different instruction sets plus non-programmable.
No, I only want one instruction set. I don't want 15 different instruction sets. I want one instruction set with the ability to call, so in the old days we used to have these EMT instructions which tracked microcode. We don't have microcode anymore. So we have these these ASICs to do a job. But at the algorithm layer, you call that ASIC when you need it, and that ASIC is replicated as many times as you need it. Does that work?
So if it's expensive to put a lot of accelerators on one chip, and then some they might not be used in some applications. But what about FPGAs? Could we put an FPGA there where you could put any accelerator you want at any time?
we could.
Yeah, look, let's talk about FPGA a bit later. So this is a very good architecture that there is proposed. The only practical issue I see with that architecture, because this was also something that we attempted in this hard project, is the type of functionality you put in this accelerator. Because it fits very nicely. You switch on the accelerator only when you need it, and then you have the customization, the specialization, so you have the best power performance ratio. The only thing is, what is this overlapping set? And A50 is a good candidate, so I agree.
There you go. So no general purpose. So you have to zoom on the different areas. You have to customize.
Yes, but then indeed, to find this subset is the very challenging issue.
What do you mean no general purpose? So everything's general purpose.
Yes, it is.
Requiring accelerators for the particular
It
functions.
will perform less for other domains.
I'm sorry?
It will perform less for other domains.
No, because you don't use those accelerators in the other domains.
Exactly.
Just
one instruction
But it's-
set, and now for your domain, you call on the accelerators that are on the chip. For your specific domain of interest, and then you get kicked off because you're done, and then the next guy gets on and calls it.
The problem is, there aren't very well identified domains. I mean, in the embedded space, there are lots of little things that people want to accelerate, so it's clear there, but it's not clear to me what you want in.
Is that true? Is that true?
That's exactly one of the questions I would like to ask to Alex, because perhaps before discussing what are the right architectures for the next supercomputer, we should start with the same question that we asked when we started with embedded systems. What is the level of variance of applications that we want to implement on these architectures? What's not clear for me is, if we are looking at a normal supercomputing center, what's the level of variance of how many different supercomputing tasks are really performed? I know from our smaller supercomputer center in Hanover, it's among top 500, but at the end, they are applying...
We're in position 180 as of June.
Ah, you know it. Okay. Not too bad, 180. And they
I'm
are
talking about
applying...
us. BSC is in position 180, is in the June list.
Ah, okay. So
don't be ashamed.
Thanks. How many different applications are you really running? Because I could imagine that on some supercomputer centers, for example, doing weather forecast or things like that, not too many different applications will run. And then for these supercomputer centers, a more specialized application-specific architecture would make sense. But for smaller ones with a greater variance and general purpose, what is running in Barcelona? How many different applications?
Over 100.
Okay. And really different?
Yes, I mean, our computer is open access, so every 6 months there's an access committee that selects from the requests.
So does anybody look at those 100 applications and try to identify commonalities? So
nothing runs on the machine that's not traced, profiled, and analyzed, yes.
No, but
you take the next step.
Everything that runs on our machine is being monitored for communication patterns, for computation patterns, for scalability.
Okay, so computation patterns. So to follow up on his question then, do you not, so here's an application 1. Here are the computation patterns. Here's application 2, 3, application 100. Here are the computation patterns. How many of these computation patterns show up in lots of cases? How many show up only on one application? Do you do that sort of thing?
We try to check for things like that, yeah. So that's how the MPI version 2 library was developed. Okay, you look at the most frequent communication patterns in applications, and that's what you support in the library. That's why you have all 12 communications, that's what you have all reduce operations.
So you say,
but that's supported in the library, but
so
not yet supported in the architecture.
So I said computation, you said communication. So computation is like a fast Fourier transform. If you capture that, does it then make sense to do this ASIC for that function? And in fact, are there a sufficiently small number of different computation patterns?
It's not sufficiently small, I would say. Okay, you have the BLAST library, you have the FFTW library. Okay, those are libraries because many applications use them. But there is a huge number of functions.
So is there any value in doing complex arithmetic instead of splitting it up for you guys?
There is a significant number of applications that do complex arithmetic. So in some cases, I think it would make sense.
Is all your inner loops DAX-B for these applications?
For complex arithmetic, you mean?
No. You said you got 100 and whatever it is applications. So that if you profile them, what do you see as the most? What's the inner loop of that stuff? What does it do?
No, I don't have that information.
So you can profile these apps and look at the.
So the thing that we look at most is at communication patterns. So I messed it up there. Okay. So we look at communication patterns, load balancing issues, and things like that. Okay, when somebody wants to run an 1000 processor and has a load balancing problem that wouldn't let you scale up beyond 64, you want to know about that before you waste 10,000 CPU hours. Okay, but then we do some analysis at the level of libraries that are used and functions that are used, but many applications have custom written inner loops, and we cannot always check that.
Okay, but this is a very interesting insight. So you say, you look at the libraries, and then of course you see that a lot of applications use this LAPAC thing, and then you say, maybe it makes sense to have accelerators for some of the functions there, right?
I mean, that's why vendors will give you optimized versions of that library. Okay, they will not do hardware specific for that, but they will give you hardware tuned versions of the software.
Yeah, even for the
Actually, Yale said that we have 1,000 cores in a chip, and actually I'm in a project that we are designing such a chip. But I don't believe,
Not surprised.
but I don't believe that you can have 1,000 cores on a chip because you have to have a bandwidth in and out. It's, unless it's something which is exposed, the one we have, that one will run.
And with that also, because they
Yeah, but basically, if we rethink this idea of accelerators and think of them as instructions at the meta level, now we have, instead of putting a lot of cores on a chip, because for me, putting many cores on a chip was a technical, it was an engineering solution to a problem which is called the memory wall. It was not a scientific solution, it was a technical,
So it's not the memory wall.
engineer,
It's not the memory wall. I'm
Oh,
tired of that. Memory wall is about latency.
Yes,
You're talking about bandwidth.
and bandwidth and latency. I mean, if you have...
Bandwidth, latency, they're two different things. Bandwidth is about...
Context switch. Context switch, I left that. But one of the things that we had because was the memory wall and the power. Now, that was an engineering solution to bring down the frequency and put 2 cores. But if we didn't solve the fundamental problem, and that's why we still have a problem with having to add huge amounts of memory per chip in order to keep the performance going. However, if we start thinking, instead of building many cores, which it seems that we cannot supply the bandwidth, maybe there is a solution, now they're talking about 3D stacking, they're talking about different things. But anyway, if we think of these accelerators as just a circuit for an instruction, like we had before, and then we start the compiler people, I know they take these patterns, that's how they work, at least the optimized compilers, they take patterns and they generate efficient code. So if we do that, maybe it's a more efficient way, we can actually, maybe we can, all of us together, write a proposal to test that. Can we just get 5, 6 different types of accelerators, put on a chip, and then get the applications that run it? Logo in Barcelona, they have their application. We go around the supercomputing centers and try to see which kind of accelerators we might come up with.
But you already have seen the accelerators that the compiler cannot efficiently use.
Right.
Okay, so if you cannot detect that you're performing the same operation on 16 consecutive data elements, let alone identify that you're performing a complex butterfly sparse reduction on a fraction of a matrix.
It's exactly, I mentioned ICTP before, and I will mention the same ICTP in 1988, and they were saying it was when the parallel machines were coming out in those days, and they started the talk, I don't remember, I think it was the guy that did, from Zambia, that did his techniques on the hypercubes. Anyway, he said that the software engineers have to learn from the hardware engineers. So you have design automation, you have everything nicely developed. The software people, they start from scratch every time, it seems. So if we create the machines and they're forced to have these regular, because most of the things are regular in these applications, just
Which applications?
these large applications. They're regular.
Are they?
Yes, I think they are.
There's a surprising number of gather-scatter operations that
Right,
consume
remember what?
a lot of resources.
Like a
We've got basically a sparse data structure.
Yeah,
That's a terminology from your era, actually.
What was that, gather, scatter? Yeah, no, I didn't hear the word that Alex said. So I want to go back to, so Alex said that, he said SIMD, and then he said butterfly. So I see those as very, very different. So I want to build on what Skevos said. So SIMD has enormous data in and out, bandwidth, whereas butterfly has a little bit of data in and out that does producer-consumer kinds of things. So it's good if the functionality produces data that's then used, as opposed to the data that needs to be used has to be constantly brought in. So with it, so I think the way Skevos wants to slice it, from what I can gather, you know, forget about latency, bandwidth, which is, you can't even deal with latency until you solve bandwidth anyway, but it's another fundamental. If you have all this functionality that's on the chip dealing with, say, one core, and now the bandwidth required is just feeding that one core and its accelerators. And now, if you've got one chip per core, one core per chip, and you've got, what do you say, 8,000 chips now we need, or I forget what the number of cores, but that's how many chips. And now you've multiplied the bandwidth by that amount, right? As opposed to putting all the cores on one chip and now all the bandwidth has to go to that chip. If each core, I'm exaggerating it to prove the point, if each core is its own chip, then you multiply that available bandwidth by that huge amount. I think that's consistent with what you were saying.
Basically, what I'm saying is that it's not an efficient way what we're doing with multi-cores right now. You know, if we see the performance we managed to get, but it's getting more difficult, and Intel came with a new terminology, many cores, because
I think you and I are on the same page.
Well,
so what about this other model?
But I would also like to go back to something Alex said, and something I've been thinking for a long time. So we have BLAS and we have Limpa, we have all this, and we have different versions. Jack Bangara, besides doing the 500, is working a lot of these things. If we basically customize, the hardware to work on these libraries, because I was with the impression that they use them. Now if they don't use them and they just write code from scratch, it's a different story.
No, they use them, but how many functions are in those libraries?
And they're simple, but they're simple stuff. If you start with plus 3, I mean it's easy, even me I can go. It's very simple stuff.
No, but I mean, how many functions are
There's
available?
over 100 functions.
Hundreds of functions.
Yes, 100 functions.
There's the FFT for 16-bit data, the FFT for 32-bit, the FFT for unsigned 32-bit, the FFT for complex 32-bit.
Yeah, and they optimize both computation and communication, right? So
do you need all those, or can the compiler help you partition the problem so that you don't need all those?
I stopped relying on compilers a while ago.
A lot of the things that you can use in the embedded space are actually standards, so they're very well defined. But there is no standard FFT. It doesn't make sense to say that, right? Unless it's part of a wireless protocol, which they said once. But for him, for Alex, it doesn't make any sense. He wants to be able to run multitude of FFT.
You can have
That's going to have different data bandwidths and
So you want to have, you have to have both the 16-bit and a 32-bit. It makes no sense to just have a 16-bit and let the compiler fix the code so that it can use that 16-bit.
if compilers worked, VLIW would have been a success.
I mean, it has been mentioned, why not use an FPGA?
yeah, exactly. That's what
No, VLIW is not a success for a lot of other reasons.
Because
VLIWs can,
compilers
no, come on. How do you get around, applications happen to have full dependencies. And VLIW sucks if there are full dependencies.
Yeah, you could say that's another aspect of that same problem.
So can I ask a question to Alex? So sorry Alex, why are FPGAs not used for these kind of things?
It's a good question.
Well, I didn't hear the question. Why are
Why are FPGAs not used for these kind of problems? I mean,
This was the
accelerate.
question of rule that I developed a little.
Right, good.
I want to come back.
Let's discuss it right now, because I'm really
So-
flabbergasted.
There was this question about why do people start using GPUs? Okay, then my response is because they promised you a 2 orders of magnitude improvement. Okay, then what people actually get is maybe a 5x. Okay, but then they invested the effort because they were promised a 100x improvement. Now FPGAs promise you a 1000x improvement. Okay, but then programming in CUDA is a lot easier than writing VHDL. Okay, so there's always this trade-off.
Yeah, but you
How much
don't have to
effort
write
is
in
it going to
VHDL.
take?
You
Yes.
don't have to write in VHDL. You have high-level synthesis, which is, okay, it's not perfect.
And also there's gigantic libraries of IP cores, especially for all the FFTs that you want. There's IP cores for that. Just pick the one you want, put it on there. Done.
Try to
Yeah, but
convince.
those cores are just like the cores that you can buy off the shelf. And it's not like you've got libraries of specialized.
Alex, didn't Cray use FPGAs on all of their machines?
Yeah, I think so.
I was not around at that time.
Yeah, Gray had a machine with.
No, it wasn't long, it was after my time. So I just found by accident.
Gray had a machine with FPGA?
Yes.
What was
Yes.
it? Did he sell any?
I don't know, but
It had the machine with FPGAs and I think
probably there was no software support for that. So that was probably the.
Yes.
And
Are
there.
you sure about that, Andy? Can we have a bet on that one?
No.
FPGAs on?
Also not aware of that.
Okay.
The Cray, tell me what you mean by Cray first.
Yeah, that's right.
The Cray company is doing one of the machines that Cray himself designed.
Cray died before FPGAs were invented. Cray died before FPGAs.
That's not.
I'm talking about the
So
configuration.
Craig didn't design the best machine that came out of Craig. The XMT.
That's correct.
I think there are questions.
Of course it's correct, otherwise I wouldn't have said it.
Well, I think there's sort of yet another dimension that we're not quite sort of discussing at the moment that's very much related to what we've said. So there's also time to market. Yeah, that is time to market for the hardware if you plan on designing an ASIC. So it may take you 2 years, if you're lucky, to build an ASIC. And think of what kind of performance increase you've seen in these 2 years by sort of a general purpose machine. And there's also time to market for the software, actually, to get the application out there. But that's the problem with the FPGA, So there have been sort of various attempts at building FPGA-based machines. If you resort to a high-level synthesis, you experience a certain drop in performance often. So it's a bit
So you're
questionable
trying
if
to
you can
explain
take off.
reality, which is, the reality is that FPGAs have not been overwhelmingly adopted for computing purposes other than prototyping and some specialized, maybe in some communications areas.
Communication.
It's not a big, look at the size of the market, it's been around for a long, long,
A
long
lot of
time.
products are first being implemented using FPGAs.
Correct, prototype, that's what I said.
Well, no, also the first
No,
editions
for
of
instance.
it. And when they see that they're sell quite okay, then they move to ASICs.
Actually, the reason I said to have accelerators and structures and other FPGAs is because of performance. Since supercomputing cares about performance, if we can, but actually a comment about that there are IP cores out there for almost for everything. So the time to market is not an issue. If we take the standard IP cores, then people would be forced to use it. If it's there, it's going to be an easy if you match it. IP cores for
What you're proposing is a less efficient implementation of the core. Does that make a lot of sense? If I stick an ARM core, if I've got a soft core that I can stick on an FPGA, it's not going to be as efficient as if it were a custom design. So that doesn't strike me as a good application, a good use of an FPGA.
The thing is that you would have a general purpose core there, and you would have an FPGA. The FPGA that you can use to accelerate a specific functionality. Put an FPGA, not the whole core, of course. And it will be slower than an ASIC, sure, of course, but you can put anything there. And you can even update it later if you have a better.
Well, that brings us back to, but I've heard this story for 20 years, and it hasn't worked. Now, why is that? There must be a reason. Either that or big, this story is like ancient history.
It's because I think there is a big gap between hardware engineers and software engineers. And it's the software engineers who do the
No, software is much more difficult than hardware. That's a big issue.
Actually,
It's much more difficult. It's bigger, it's more complex. There are thousands of, for every piece of hardware, there are thousands of people that program, literally. And thousands of different things, right? Because you've got a general purpose base. I mean, Microsoft, look at the size of the companies that are out there.
And how many of
They
them,
do software, they don't do hardware.
and how many of them know what the hell they're doing?
That's a separate question.
No, but I think that's at the heart of the issue.
Actually, that was my question to Alex. I think you are the only supercomputer I know that is run by computer scientists is the Barcelona. Most of the supercomputers is not, it's good that it's run by computer scientists, but most of the other supercomputers are run by scientists that sometimes they give talks and they don't really know the standard architecture. You know, I attended the talk of
They probably don't know the difference between bandwidth and latency.
Yeah, exactly.
That's acceptable.
No, just a second. By the way, Trevor, you just did actually very good advocating for FPGAs. You say hardware is easier than software, so why not go and implement all this functionality in reconfigurable hardware?
Because
then you get rid of the software.
it's predicated on a lot of software. The problem with the FPGA is, in fact, you need more software than if you targeted a general purpose. It's the level of abstraction. It's a lower level of abstraction.
More design effort. But by the way, there is some example that may prove that this funny technology may work also for machines. You know about the Maxwell company, Oscar and Mike Flynn started in London. So they
I don't know about it.
Okay, we'll talk about it. So they made their own hardware, so they are completely FPGA based. So basically they even don't have the general purpose processor. So it's full FPGA based machine. They understood the importance of a lot of on-plate memory. They understood the importance of very high bandwidth and low latency communication between these FPGAs and the memory. Yeah. And of course, the biggest pain is how to basically map the algorithms of their customers to this platform. Yeah. And they spend a lot of time on designing that. And that's why they're basically in huge need of very clever hardware designers.
So at the risk of giving you more ammunition for this, this concept of FPGAs, I want to Convey. You familiar with Convey? It's the Wallace new company. So what they've done is they've put these massive FPGAs on the chip for the purpose of interfacing the processor to the memory system.
They will learn better, yeah. They integrated the memory system.
And by doing that, they're supposed to get a lot of performance. But
Yeah.
I like Trevor. I've been hearing this story for 20 years.
I've been hearing this story. Now I'm
Can I just say
perfectly,
something about
I'm
this?
perfectly prepared to be proven wrong, but if I remember correctly, FPGAs were around before cell phones. And cell phone, that thing sort of grown, right? It's been a success, it's a good idea, fit together, What happens to FPGAs?
Well,
If I'd have invested in Nokia versus an FPGA company, I'd be a rich man. And
when you find an application that kids will start calling together or doing something.
well, all I'm saying is
FPGAs.
I don't see a compelling application that has significant volume for this. And the same arguments have been trotted out. Now maybe they're right. Maybe something will happen that makes it all fit into place, but we just don't see it. I think it's too complicated to deal with. That's the problem.
Actually, that's the point I was trying to make, because mentioning Mike Flynn, I remember when Mike Flynn came to the university I was teaching, and I asked him, how come you did this classification of different parallel models? What was the motivation? He said, I saw ILIAC 4, so parallel processing was imminent, would be in the mainstream, so I thought it's a good idea to come up with these models. And it took how many years? 67 was ILIAC 4. It took almost 40 years before we have basically parallel processing or attempting to have parallel processing mainstream.
No.
We're attempting. The mathematics
Vector processing.
No, no, in mainstream.
Vector processing is an
Yes,
an
yes.
instance of SIFTing.
No, mainstream, I'm talking about everyone is using. That was a problem why when they.
Well, that's
when
not
they-
even because of the applications.
Yes.
We've got things like video today
That's
that
right.
everybody uses.
Yes.
It's not that we
Exactly
didn't
right.
use them then, it's just that not very many people use them. I mean, I've worked on it for graduate school when that was a project at Yale.
What I'm trying to say is that maybe they, maybe we hear it for 20 years, but we were hearing things for 40 years before they start becoming mainstream.
That's more a case of integration. I mean, you can say the same thing about computers themselves. I mean, you can take an Iliad 4 type thing, stick it on the corner of a chip to it.
Color.
The question that Annie asked, I think that this question can be answered from the other side. We asked ourselves, why are not FPGA included in supercomputers? I could imagine, it's a little bit speculative, but that, for example, those companies that today build FPGA-based emulators, they go over to the supercomputing domain. Okay, still they are some orders of magnitude away from it, but for example, when we bought some weeks ago our new FPGA-based emulator, we had a presentation by Berkeley Emulation Engine Company, and they showed us, for example, in the ASIC emulation domain in companies like Intel and so on, they are using supercomputer-like clusters of hundreds, thousands of FPGAs today.
Yeah, most companies
It's more
build
application specific, but they are testing several things on them, and we have also seen FPGA-based emulation machines for weather forecasts and
But
things
that's
like
not a
that.
volume, that's sort of a niche, isn't it? Building emulators for
The
guys.
supercomputer is also a niche.
Yeah, it is,
Yeah.
absolutely.
So, and I can imagine, and it's the same that we had in
I'm not
heterogeneous
arguing that.
architectures.
It is,
That
yeah.
First of all, processor designers started to include
So here's an area where-
accelerators, and then FPGA companies started to include soft cores and hard cores and so on. And I could imagine that in some years, in several years, there could be a rival for supercomputers coming from the FPGA domain.
So if you can run your, if you can emulate a core with your FPGA and you can run some security software on it, you've immediately cracked it because you can watch it execute. So in that sense, that's one application that I haven't seen much of, which strikes me as a good one. You can actually break any code by taking, the core that it runs on, making an FPGA version, and then examining the operation. So that's why some of these big SAMOS chips have sort of this almost security level associated with it.
I'm gonna cut it.
Carlos.
Can I have 5 minutes more? In 15 minutes, the bus will be here in 15 minutes.
The bus will be here in 2 minutes?
In 15 minutes.
15 minutes.
So if you want 5 minutes more, go ahead.
But you guys haven't answered the question why FPGAs have not come.
Yeah, look, if you spend the effort to port these 100 applications that Barcelona Supercomputing Center is having to the platform,
Luigi.
Young man.
really,
What?
FPGAs, they give too much power.
no.
Yes.
We disagree on that, Luigi. Actually, you have to rate it to the...
We have a young man who's being polite, so we should
Yes.
have a talk.
Okay, thank you. So it's my sort of, let's say, personal attempt at answering Trevor's question. I feel if you've developed your FPGA and you've optimized everything, you've gone about 3/4 of the way of designing an ASIC or an ASIC. Yeah, so why bother then? Yeah, so you go a little bit further and you've got something that's even more power efficient, faster, it's smaller in areas. So I feel the FPGA takes a whole lot of stuff to optimize. So you're very close to an ASIC already. So if it falls into a certain particular niche, and then the ASIC wins eventually again. Reuse.
Reuse, yeah, you already have the supercomputer.
Sure, but you can
You
apply the
develop- you
reuse of
develop
IP to the ASIC. Yeah, if you've got the IP block, stick it onto the ASIC, and off you go.
So going back to an earlier point, it's certainly true that most CPU manufacturers build an FPGA version. They have one sitting around. I happen to have one to use.
Me too.
For a fairly well-known architecture, but it's, but you're not gonna, you do, the thing is a complete design, so they've completed the design except for, you know, the circuits. There's a lot of stuff that goes below, the abstraction of a logic gate is only the beginning, actually, if you're going to build a really efficient ASIC, right? And you don't have that choice in FPGA. Everything is handed to you. You can't optimize that level. So you have, you know, you have a lot of knobs that you can't turn on the circuit. And then if we go back to another point that we haven't touched on, memory. The memory of the system is really where the energy is going and where the cost is going. It sort of leaves the FPGA out to the side, right? But you're all making it. This reminds me of going into a room full of people who think that asynchronous circuits are a good idea, you know. But they've been around for years too, and they're a little bit more extreme in my opinion. It doesn't matter what happens, they've got a solution. But there's no evidence that it's a good idea. And so that's my point. If it were a good thing, we'd see it all over the place. We don't. There's 600 million of these things around. They don't have FPGAs. Why is that?
Fantastic. Well, now I agree with you. For this kind of application, for sure. But when you can optimize your data path to the computation between.
That's right. So Alex will be building his supercomputers out components of these things. Because they'll be so cost effective. And they're always designed for low power.
In that way, I mean, do you think that the IBM PC was the best platform? That's why it's everywhere.
Well, you're making a different argument, which is not an engineering argument. You're making a scientific argument, which says the best, we should do the best.
Let me guess what
do the best
Alex want to say. Alex.
Oh, no, it's not on this one. So maybe the reason why there are no FPGAs in supercomputing is because there have been a couple of attempts that really did not do the right thing. So people wasted enormous money and effort on them. So I'm thinking of the example that we have in our computer room, which is the Altics.
Yeah,
okay, we spent a significant amount of money on the FPGA blades for that machine. We spent a significant amount of time trying to program them.
You guys are not talking to the embedded people, so that's important. You know, and they put it in a separate
people who have tried,
memory space.
either they did not try hard enough or they couldn't get it right. But there have been attempts and it just didn't work.
You know, in contrast to that.
One correction there. So, Trev, you were saying that FPGAs are not being used in small devices over here, but that's not true.
Okay.
I mean, there are phones using FPGAs. I mean, Ollie doesn't want to sort of raise this issue, but they are.
That's also true. Professor Penry wanted to speak.
I program abilities that the design problem was the reason we can't get FPGAs in the supercomputing center. So I've been trying to get our local supercomputing center to get one node that had an FPGA sitting there on the front side bus. And they could find no other users of this computer who wanted even one node that looked like that, because all of them say, why in the world would I want to do hardware design? I have science to do.
How many nodes are there?
A couple thousand.
And they wouldn't give you one node.
And no one's interested.
No. What do you mean no one's interested?
No one is interested in.
I thought you were interested.
What?
No,
I thought you were interested.
Okay, yeah, but I'm no one.
So the supercomputing center is run by scientists or by engineers?
By scientists.
I think that's
what
one of the main
Skevos is
problems, because we started one in Cyprus, which is our supercomputing center. Don't ask me why. We just blew up our only power plant. And it's a scientist, and I know them, they're in my department. And I'm not sure they understand, the fundamental things about computing.
What do you mean you're not sure they understand?
Fundamental, very fundamental.
You're not sure they understand the fundamentals?
Yes.
You are sure they
Yes,
don't
I'm sure
understand.
I remember, how many of you remember the convex? I had some friends in the OR group of my department that they were using the convex for parallel processing of because of the. So one day he comes to my office and says, I go to 10 cores, 10 processors, speed up linear. I go to 12, drops down to 0 speed up. So I asked him a few questions and I realized he was using a matrix which was fixed. So I said, how about if you make two copies, A and B, and make it that the one hits the other, odd even. The next day he was hugging me. oh, we have linear speed and now we can publish our results. Because they didn't understand memory contention. That something happened when we added one more core, and they didn't understand it. So that's why we have supercomputers which don't make sense. Because they're basically run by scientists. For some scientists, like Jeffrey Fox, it's an exception.
It takes a PhD in computer architecture to program these machines.
No, actually, it's not enough.
That's why.
It's not enough. That's why
it takes a special type of PhD in architecture to program a machine like this with FPGAs. So that's why.
So we have one.
No. Less than.
We have half here.
So is that really true, or is it that there are too many, that there are too many people that are just clueless about what's going on across the spectrum? And it may not even be just the scientists. Shouldn't, and I realize that I'm opening up a very different envelope here, but isn't it time that computer technology join mathematics and physics as a core competency for everybody who purports to contribute in this larger domain
Where do I have to
called
sign
science
for that?
and engineering?
So maybe that's a good
Where do I
topic
have to
for
sign for that?
I'm sorry?
Where do I have to sign for that? Because you can teach physics to a computer architect, but you cannot teach architecture to a physicist.
So
Hey, I have a physics
so the idea is, be careful, if you get the physicist when he's a freshman, before he realizes he's a physicist, then maybe you can teach him computer architecture.
Actually, I have a more fundamental question, and I'm serious about it. I read.
Oh, no, I was serious about it.
I was not referring to you. I'm saying.
I would like to see computer technology be a core
Yes, no, I agree
competency
with you. I agree
in
with you.
addition to mathematics and physics, period.
And I was in a committee in Cyprus to put it in the high school, and I was fighting for it. And in elementary school, they are doing some things. But I think it is a more fundamental question to me when I read Peter Kogi's report on the exascale that was part of that. There was all these things there. One thing caught my eye in the summary, which I basically searched the report and I couldn't find it. It said that only 7% of the time all the cores are used. So I was wondering if that's the case, then why do you need to put an exascale computer and don't build a few smaller ones that they will be, doing it? I mean, it's most like a status symbol. It seems to me. If that efficiency, if that report is correct, because I saw it only on the IEEE magazine or Spectrum, I don't remember which one of it, I downloaded it, and I gave it to my students, and then I realized, I told them, tell me what you think is strange in that report. And of course no one said what I expected, so I went and got the whole report, and I only used PDF search, and I couldn't find that number again, because I was trying to see why this is happening.
7%.
There is a 7%, I probably have it on my laptop.
So why don't you just build the 7%?
That's what I mean. Many 7%.
Because you'll never get an impact to be in the top 500 if you only have 7% of the core.
You blow the 7%.
Yeah, I've saw the same number, I've heard it quoted many times, I don't know where it's coming from, because it's not true. If the application only used 7% of the cores, I would just tell the user, I'm giving you 32 cores, no matter how many cores you're asking me for.
Actually, I use less than half of my brain.
Guys, I'm sorry, but I think we have to finish.
Oh, yeah.
And I would like to make a remark, is that the force will have not answered any question at the end.
Okay,
So,
but tomorrow.
Try tomorrow to start.
You're prepared for tomorrow.
Whoa. Why is that a relevant remark?